Hello everyone. So this is Dilipkumar. So the past videos we have seen the basic concepts that can be useful in electromagnetic theory, that is a vector algebra. So we have seen vector algebra concepts. So in this video we can see coordinate systems and transformation from one system to other system. So generally, a point or a vector can be represented in any curvilinear coordinate system, which may be orthogonal or non-orthogonal. So orthogonal in the sense perpendicular to each other, perpendicular in nature. That is the axis. If you take the x-axis or y-axis, if both are perpendicular, it is also orthogonal. Or if you take a three-dimensional case, x, y, z, all the three has to be maintained among themselves with 90 degrees, then it is orthogonal system. So an orthogonal system is one in which the coordinates are mutually perpendicular. Generally we can able to see there are so many Cartesian, there are so many coordinate systems. So simply to say here, you can able to see that is a Cartesian or rectangular system. This is the one. Another type to see circular cylindrical. This is other type of coordinate system. And the other one spherical. Next elliptical cylindrical. Next parabolic cylindrical, conical, and even so many we can able to see the different coordinate system. But there are three main coordinate systems that are helpful for the sake of very much useful in electromagnetic fields. That is Cartesian or rectangular coordinate system, circular cylindrical coordinate system, and spherical coordinate system. So these three is very much useful in most of the cases of the electric fields. So we will see one by one these three, that is Cartesian rectangular, circular cylindrical, spherical coordinate system, in this session one by one. So first we will look into the first one, Cartesian coordinate system. So Cartesian coordinate system, Cartesian coordinates. So Cartesian coordinates we generally used with the parameters x, y, z. X, y, z we will consider. So in order to represent any point in this free space in the Cartesian system, we use these variables x, y, z. Let it be, if you want to represent a point P, it is to be represented with the parameters x, y, z axis. So what about the ranges of x, y, z? X, y, z ranges. X is ranging from minus infinity to plus infinity, and y is also the similar range, that is minus infinity to plus infinity, and z is also the similar range, that is minus infinity to plus infinity. And if you want to represent a vector in Cartesian system, as to represent, suppose a vector has to be represented in a Cartesian system, that is to be represented in the form of a point. Suppose if you want to represent in the form of a point, that is ax comma ay comma az. If you want to represent in the form of an equation with unit vector ax into ax plus ay into ay plus az into az. So here, in order to represent your the small variables, that is small scaling factors ax, small ay, small az. These three are unit vectors of the respective axis, and ax, ay, az, these are the products of the respective unit vectors. And what about x, y, z? These are called the specific directions in that respective coordinate system. This is about Cartesian coordinate system, where the point is represented in the form of x, y, z. So the next system we can see, that is circular cylindrical coordinate system. So this system is, let me write the name of this system, circular cylindrical coordinates, where the parameters is to represent in the form of a point with the value parameters rho, phi, z. These are the three parameters that we use in circular cylindrical coordinates rho, phi, z. So the name it is obtained for this system because the shape of the system is looks like to be a cylindrical in shape, which has certain height, and it is in a circular shape. That is why the name it is called circular cylindrical, and the coordinates is represented with rho, phi, z. So the point P in this system is represented with rho, phi, z. Now let us see what are these names are called. So first is to see rho is nothing but it is the radius of the cylinder passing through P. So if you see this diagram, it clearly mentions that it has been starting from the axis point. Suppose on the z axis it has been started and the center, and has been moving towards, passing towards P. I hope you can able to follow this green line which I am drawing. The green line is pointing towards P, passing through P. This distance is called radius of the cylinder passing through P. Here the radial distance from the z axis that you need to remember. Then the other parameter, that is the phi parameter, which is called azimuthal angle. Azimuthal angle. So here azimuthal angle is measured from x-axis in the xy plane. So in order to see, this is the xy plane. Okay, so this is the xy plane. Okay, this is your xy plane. In this plane, if you take the angle, from the axis of the x, towards the y, if you move, whatever the angle made with this passing through, if you and in order to have the particular angle, first you need to project point P onto the plane of xy. Then let me show you in a clear manner. So whatever the point you have been projected, you can project the same point P here. Then you draw a line onto this from center horizon O onto this circular cylindrical surface. Then if you made an angle, this angle is called azimuthal angle. This azimuthal angle is to be taken only on XY plane. Then the z, the third coordinate is z. Z is the same as in Cartesian system that was seen in the previous system, Cartesian system. Okay. Now let's look into the ranges, how these ranges will be. Okay, so first coordinate, that is a rho, is that is the radius of the cylinder, 0 less than or equal to rho. less than infinity. Then second coordinate range 0 less than or equal to 5 less than 2 pi. So which is nothing but 360 degrees. Obviously the circular shape of the cylinder around is 360. Obviously the angle is also from 0 to maximum of 360 will be there. Then the z axis is the same as the previous Cartesian system, which is nothing but minus infinity to plus infinity. These are the ranges. Okay, now let's look into the coordinate the coordinates with respect to what to say, your vector representation in cylindrical coordinates. So vector representation, let us consider a bar. So the coordinates with respect to vector a bar is a rho, a phi, a z, and the equation will be a rho plus a phi plus a z. And if you want to take the magnitude of this, then you will get the term a bar equal to modulus root of a rho square plus a phi square plus a z square. Obviously, if you take the product square of the each individual term, the unit vectors will be 1. How it is become 1? You can check out the vector algebra video so that you can able to understand why the product of two unit vectors in dot product it is 1. There you can see with respect to dot product explanation. So here we can see the unit vectors a rho, a phi, az. All the three unit vectors are also mutually perpendicular. Obviously, in the initial concept of the coordinate system, it is mentioned that all the systems which are described in this video is belongs to orthogonal systems. Unit vector dot products of all these dot products, all these equal to 1, and alternate, individual same co-dot products is 1, and alternate dot products is, that is arrow dot a5 is 0, and cross products you will get opposite unit vector. So that is let me take one example. Arrow cross a5 is equal to az, and arrow dot arrow is equal to 1, arrow dot a5 equal to 0. So the different examples I am writing related to this one, that is the dot product by the dot product for the same coordinate axis one, dot product of the unit vectors of the different coordinates is 0, and both are mutually perpendicular. All the three are mutually perpendicular to each other. Now let's look into the next one. Here, if you see, this is the transformation, some transformation, sorry. Here you can here you can able to see there is a relationship between how you need to relate the Cartesian coordinate system and circular cylindrical system in the same coordinates or in the same axis, how to relate those two. So first coordinates which is represented here xyz is Cartesian, rho phi z belongs to circular cylindrical. So the point P has been represented here is in a free space, and we need to give a relation between the two systems, Cartesian as well circular cylindrical. So if this is the axis of the x, this is the axis of the x, and it is the distance, we can able to consider it as x, small x, and this distance, that is this distance you can able to consider it as, that is this let me draw the line. This line you can consider as small y, and this distance is small x, and as this one is parallel to this one, this x is equal to the same this x, and this one is parallel to this one, and this value is the same this value is this term y. Okay, now if whatever the angle made from the center of the horizon to this point projected onto xy plane, this angle is phi, which is called azimuthal angle, and rho is called radius of the circular cylinder, and which is the distance is rho has been mentioned here. Then how can you get the value of x? If you apply the trigonometric functions, normal basic trigonometric functions from this using the angle and this right angle triangle, then you will get the value of sine phi equal to y by rho, which is y equal to rho sine phi. So this is what has been mentioned here. Then the other term, that is cos phi, of course sin phi is nothing but opposite side by hypotenuse, cos phi adjacent side. So with respect to this angle, adjacent side is x1 x, so that is x divided by rho, which is nothing but x equal to rho cos phi. Okay, so this is what has been mentioned here, and this is what mentioned here in this term. Okay, both the terms you can able to see. Now the relationship between the variables x, y, z of the Cartesian system and those of the cylindrical system rho phi z, how you will get both the relations in other terminologies. That is, using right angle triangle, rho equal to, you can able to write, give the relation between x and y and rho phi z, x square plus y square, x equal to rho cos phi, and here phi equal to tan inverse of y by z, and here y equal to rho sine phi. In both the cases, that is in this terminologies, both the cases z equal to z, there is no change, because obviously that has been mentioned earlier that the z value is the same in Cartesian as well circular cylindrical system. This is how we can give a relationship between your Cartesian system as well circular cylindrical. Okay, so like this you can able to relate both Cartesian as well circular cylindrical in the exams. Based on the question, you can able to substitute the values of xyz or rho phi z in order to convert from one system to other system between Cartesian as well circular cylindrical. Now we will look into the how the transformation will be takes place with respect to unit vectors instead of coordinates. We can see how the unit vectors can able to relate. Let's look into that. So here is the relation. You can able to see the figures, both the figures, where one figure, the first figure shows cylindrical components, that is AX, AY, AZ. It is related to A rho, A phi, AZ. Then in the second figure, cylindrical components like A rho, A phi, AZ, which is related to AX, A phi, AZ. Now we will write the relation or the equations how to get one system to other system. So let me write the first coordinates with respect to unit vectors AX, AY, AZ, and here A rho, A phi, AZ. Now, if you see the first equation as how we applied the trigonometric functions in the previous slide to relate with respect to the coordinates of x, y, and rho, z, the same manner if we apply here with respect to this figure, then we can get the equations, the relation ax equal to cos phi a rho minus sin phi a phi and ay equal to sin phi a rho plus cos phi a phi. So you can able to get the easily from this figure these relations. No need to worry about, because here the last term az will be the same. However, the same thing happened in the previous case. You can apply the cos phi equal to cos phi term, that is the adjacent side. Up to this partition you need to apply ay by the term 2a5. Like that, if you apply the total term, the relation, then we can get these relations. Similarly, on the right hand side for the cylindrical components, a rho equal to cos phi ax plus sin phi ay, then a phi equal to minus sin phi ax plus cos phi ay. The last term az will be the same as it is, az equal to az. There is no change in it. Now, the same relations we can able to write either in terms of matrix representations also. That is also we will see now. Okay. So in order to represent in the form of a matrix, I am writing now. Please check it here. The left hand side, if you take a rho, a phi, az, there is a vector representation equal to cos phi sin phi 0 minus sin phi cos phi 0 0 0 1. And what the term to be get on the right side of this equation? Alternately, we get on the left hand side of the equation is cylindrical. So obviously we will get the default case Cartesian we will get. Similarly, we can able to write for the other coordinates. It is alternate manner ax, ay, az, left hand side, that is equal to here right hand side cos phi minus sin phi 0 sin phi cos phi 0 0 0 1, and the term here the unit vectors a rho a phi az is about we will get in the form of a matrix representation. From here this relation, that is this one is relation between Cartesian to cylindrical, circular cylindrical. This relation is circular cylindrical to Cartesian. Okay, these are both the relations that has been shown here. Now we will move on to the next one, that is spherical coordinates. We will look on to the spherical coordinates now. Here, however, the coordinates for Cartesian xyz, circular cylindrical rho phi z, here the coordinates are not represented in the form of a point, that is r, theta, phi. Here r is nothing but the radius of the sphere, theta is called elevation angle, that is taken from the z-axis towards the point P of this line. I hope you can all able to see this cursor where I am pointing. This is the z-axis, x-axis, x, y. z-axis. Here the first one is first coordinate r, which is nothing but from the center to point P, where if you make a draw a line, where you can able to draw a line, this line is called r, and it is the distance or the radius of the sphere, and theta is the elevation angle which is taken in vertical plane only. Elevation angle is to be taken, that is the theta, and it is taken from the z-axis towards the line joining of O to P. Then the other coordinate, the last one, that is phi, it is the same as been taken in the previous case of the circular cylindrical. Here this is called azimuthal angle, which is taken from x towards y moving, and it is taken only in azimuthal plane or in a horizontal plane. Now we will look into the ranges, how the ranges are for these three coordinates. First one, r is range from 0 less than or equal to r less than infinity, and for the theta, 0 less than or equal to theta less than or equal to pi, and phi azimuthal angle, that is 0 less than or equal to phi less than 2 pi. This is about, and the vector representation, let's look about ar, a theta, a phi, and expression ar and small a plus a theta small a theta plus a phi small a phi, and you can able to write the magnitude, there is no problem. Obviously you can able to write the dot products also, same dot product unit vector results as 1, different unit vector product results 0, and the cross product results opposite vector. Obviously here also all the three are perpendicular to each other, that is orthogonal in nature. Okay, that is this spherical coordinates. Now let's look into the relation between all the three. Let's look into that. This is what we have been uh, just now mentioned the name, that is a relation between Cartesian coordinate system, circular cylindrical coordinate system, and spherical coordinate system. Here obviously between these two relations we already seen. Now additionally we have been added this one, it is spherical one also, that is r theta phi. Now if you see this figure, all these relations you can easily see. So this is the distance of x, this is the distance of y, this is the distance of z, parallel. These two we can, you know, already the same manner we can able to get the remaining terms. It is this term is z, this term is z, this is a parallel, so this is also z. So the same manner how we got in the previous case cos phi sin phi, the same manner you can able to implement the same thing here also. Just take it as a small exercise so that you can get easily this practice. If you want I'll give, so that is a small thing. I'll mention this one. Cos theta is nothing but adjacent side, so this is the angle theta. Adjacent side is nothing but z, and by hypotenuse, this is the hypotenuse, this is nothing but r. So by default I can get z equal to r cos theta. This is how I got this expression. In the same manner you can able to get the remaining expressions by doing a small simplification, a small calculating from this figure using trigonometric functions. Now in order to get the relation between spherical and Cartesian, let's write the equations. X equal to r sine theta cos phi. This is how we got, very simple manner. So if I write x equal to rho cos phi, if you substitute the value of r, sorry, here I wrote it is phi, it is phi. Here x equal to rho cos phi, from this you can able to get it cos phi. If you substitute the value of rho, which is nothing but r sine theta, we will get this expression once again. Okay. In the same manner we can get y equal to r sine theta sine phi, and z equal to r cos theta. And what about the remaining? That is opposite, that is from, if you have the values of Cartesian, then you need the system, Cartesian system into spherical, then you need to substitute those values here. R equal to x square plus y square plus z square, and theta equal to tan inverse of root of x square plus y square by z, and phi equal to tan inverse of y by x. This is how we can see, that is a relationship between Cartesian and circular cylindrical as well spherical systems. Okay. Now, in the same manner as how we have been mentioned, we can go ahead with the unit vectors also. That is also possible in this case. Okay. Now let's look into the shapes, how it has been constant shapes, phases are there, and how it looks to be. If you see, these are the constant uh, surfaces, shapes you can easily identify. If you have some plane sheets has been mentioned to represent, see, let me show you. So let me show you this. So here, this is a center point origin. This is center point horizon. Okay. Now there are three different, or maybe three same size of sheets has been placed. One sheet has been placed in one plane. That is, let me take this plane. Okay, this surface. This surface has been placed in the plane of which plane? This is ZY plane, and this surface has been plane. Sorry, this is the same, right? And this surface, this one has been placed in which plane? XY plane. And there is another sheet, this one, this plane. Okay, this one, this sheet has been in XZ plane. Now if this plane has been, I mean the sheets are, surface sheets are being placed in a particular planes, then by default the other coordinate will be constant. Here x, I mean z, y, it is a plane. Now x is constant, and if you see this one, that is xy plane, z is constant. Then this case xz plane, y is constant. The same you can implement this one in circular cylindrical as well, even in spherical coordinates also. The same thing you can able to see. Just see, phi is constant where it is a plane of rho and z, and here z is constant where it is the plane of rho and phi, and here the rho is constant which is the plane of phi and z. This is about whichever the plane we are talking, plane belongs to two coordinates. Two coordinates will be variable. If two coordinates are variable, one coordinate will be the constant by default. Okay. Now the same concept of constant surfaces look into the spherical. If you look into this here spherical, see, three coordinates r theta phi. If phi is constant, r theta is variable. Now the sheet is in r theta plane. If theta is constant, it is in the plane of r phi, r phi. See, there is r is value, sir, and I mean phi is also variable, which is nothing but horizontal plane, azimuthal plane, and the other last coordinate r is constant, theta and phi. Elevation is exist, even r is, I mean elevation is exist and azimuthal is also exist. This is how the uh, description relates to Cartesian coordinate system, circular cylindrical system, and spherical system, then the relationship between individual coordinate systems. Thank you. All the best. Thank you.